and I'm very happy to welcome Brian Sellar, if you'd like to come up to the stage, please. As you know, that we're hosted by University of Edinburgh in this fantastic facility, and we're very happy with that. You can see a few members from Edinburgh University dotted around. Brian is here to represent the university and be talking about
combined measurement and modelling.
Perfect. Yep. Brilliant. Okay, thank you very much, Brian. Off you go.
Okay. Well, thanks very much for the introduction. Hi, everyone. Really happy to be here. Thanks again for the invitation. I'm going to talk about combined measurement and modelling for offshore renewable energy. I'm based at the School of Engineering, University of Edinburgh. Let's see if the clicker works. The subtitle really is about getting the right data at the right time from the right place, really. So we'll talk about those 3 points, and then we'll do a case study on some advanced sensing. And all of this is about getting tools to try and accelerate offshore renewable energy. So we probably hopefully have time to do a little bit more detail towards the end, and we'll just do an overview at the start. So why do we need data? To reduce technical risks, to reduce costs, and to ensure sustainability. We do a lot of work collecting data to try and increase reliability, to improve performance, scalability in terms of are we going to be ready for going to arrays, and to check that we can mitigate any potential hazards. So sort of looking forward all the time. Now, how can we get data? So we've got data, time and place. The data itself can come from many ways. We've got lots of different ways to do it. And I started off as a specialist in subsea sensing, but with all the projects we've been working on, you start to see the data as just inputs that need organised, really. We've got structural laboratory facilities, so places like Fastblade, we need them to do large-scale component testing. We've got advanced measurement, which we'll talk about later, working clockwise from the yellow circle. We've got regional scale models. These form an important part of the puzzle. We can look at take advantage rather of upcoming AI, machine learning techniques. We need the electrical system modelled in there as well. There's further data around that. I tend to concentrate on the fluids and the machine response, whether it's wave or tidal. But actually, it's all about, we really care about when you get your phone charged. It's the electricity at the end that we're interested in. We can do ecological sensing and sort of standard drops. We need CFD in there, well, numerical simulation. Are we talking about 10-minute simulation runs that take a month on a supercomputer? Or are we talking about desktop applications that can run 1,000 simulations in a day? There's quite a big difference. And then we get into physical testing, like tank testing, that we'll also touch on because I do a fair bit of work there. And what we're increasingly doing is joining these up. We need to look in the whole. The teams that we're working with are increasingly multidisciplinary, and we're really channeling and funneling and converting data between all of these inputs. So that's where most of my research is spent at the moment. And the sort of lessons learned since about 2012 working on industrial academic projects in this area has been that there is no single solution. There's no silver bullet in terms of measurement. There's no silver bullet in terms of modelling. And when people need different data at different times. A developer might just want a fast model run, and not having that could be causing them big problems. And then at some point, the phone you might ring, and now you need the high-resolution simulation run. And that's all controlled by a lot of things are external. It could be finance, it could be government announcements, and that's so we really need to think about a roadmap of data if we can, and sort of think holistically. A little bit of a cartoon here in terms of we've got data timing. We've got to think about when do we need it? Do you need it streamed? Do you need it in a sort of few weeks? Or can you wait until after winter? And my team and I have worked on projects where we've done all of that. We've had hardwired connections to 1 megawatt machines in the sea that we can operate from our office. And we've had packs that are just loaded with batteries, and we just hope that they'll last the winter and we'll get them back when we can next get out there, because these are quite extreme environments. And we've done things in between. And then in terms of the processes, certainly on tidal as an example, we're dealing with coupled systems. We've got timescales of tides that are changing from 6 hours to daily, fortnightly, monthly, all affecting design and operation, weather windows and things like that. Then we've got turbulence timescales, seconds to minutes, large eddies that are shed off of islands, and then we've got waves on top, and they're also happening around the sort of 10 seconds stage, and that's mixed in with the turbulence signals. So how do we decouple that? How do we understand that? How do we measure that? Hopefully, so if I'll pause here before I start this animation. That's the cartoon on the left. On the right is some measurements we took. And this is a visualization of real data. We're going from the seabed down at the bottom here up to about 45 meters depth. This is data from the European Marine Energy Centre. We're going to be running in time, so it's going to animate. So I just wanted to pause here before we start, get confusing. Red will be in towards us, and this is velocity variations happening live, if you like. Blue will be going the other way, velocity deficits. And these are the sort of environments that a machine will operate in. Hopefully it'll play. The grey line that you can see going up is the sort of theoretical. It's actually the mean. It's not the theoretical. It's the average in time. So talking about what sort of time do we need. We've collected this for 2 months at about 1, 2, 4 hertz, something like that. And then we want to take statistical averages or get statistical descriptions of the data so we can use it for design. So at any 1 minute, we're not really on that average. Any second, we're varying a lot. If we move on and ask a question, okay, about place or data space, that's great. We know about this location. What about if we go over there? We've done that too, and this leads us on to the requirement for modelling. If we take the data from 45 metres southwest of an operating tidal turbine, and we take data from 45 metres northeast, we get very different profiles. And this was a research finding 2015, right at the end of a project where we went, uh-oh, this is even more spatially variable than we thought. If only we had a model, which we didn't because we think we used to work in silos a little bit more. This shows us that we really need to fill in the gaps spatially as well. So the data is excellent for one location, but what happens when you go somewhere else? This also has consequences to the type of machine. So this is just flow data at the moment, but what you really need to ask is, are we an orbital, for example, machine in the top part of this, or are we maybe used to be an Alstom machine in the middle, or are we maybe a Sibella small machine or a Nova, something like that, down the bottom? So again, you need to think, this is just the environment, what happens when we put machines in there. So what we have been able to do is with our projects is go back round, build models. We developed modelling techniques on various projects, resource code, real tide and fast water, Oceanera Net, Horizon 2020 and UK Supergen ORE hub monies. And we were able to say, okay, we got the data from 2015, what was causing that? And I think it should just play the blue, we're looking at flow rotation here, and you can actually see that one of the instruments is right on the edge of a really dynamic part of the channel. So it just so happens we did all our experiments, £12 million project on ETI readapt, slightly to the left of a dynamic part. Had we moved that, or if EMEX berth was slightly further to the northeast, we would have whole different type of results and understanding. So clearly we need to couple these things, hopefully, as they take home. We're extending that now. We're working with Maygen, looking at 3D models of their site, and it's quite timely because of recent announcements about the CFD round 4 and the push to say, okay, how can we go and start thinking about large-scale arrays? And you're not going to be able to dodge the interest in areas of the channel just by picking the odd nice spot. We're going to have to understand the full 3D flow field. This is our outputs from a work over probably the last 10 years. It mirrors that idea of joined up measurement and modelling. Starting from the top left, we can see data feeds, as you saw. Data basing and data access, data management is a huge part of it. It's got so big we can't do it ourselves. The school is a very big school, and for us, we're now working with the Edinburgh International Data Facility to try and homogenise our systems. We're telling them all the things we've done in lessons learned and data headaches we've had, and they're now strategically helping us with that. So we're transferring all of our data tools, if you like, to a central partner. That's ongoing. Frequently working with CFD people, saying, working on specification. What do you need? Because if you don't need it, we won't spend time prioritising it in the field to measure it if you can't use it in your simulation. Lots of coordination work in test tanks over the years, bottom right. Data classification, again, we don't want to just know about one place. We want to be able to make some guidance and sort of extrapolations to other places and other sites. So trying to characterize all this data. And then we get back round to regional modelling and advanced sensing, which we'll jump onto now with the remaining time. Okay, so you saw the depth profile of velocity. That was measured by an ADCP, an acoustic current Doppler profiler. You can see one of them here, the 4-beam red transducer sitting on top of the Sibella turbine. That was on a project we've just completed called Realtide. They're typically put down the bottom, they're placed on the bottom, they profile from around about a metre above the instrument all the way to the surface. What's interesting is the data quality varies with space. So very good down low, strong signals, gets higher up, lots more interference. The beams are spreading out to build this profile, and then certain assumptions of their operation start to get a little bit, more wobbly at that point. So a question is about the uncertainty of those measurements. If we're using these measurements to validate and calibrate numerical models, which we need, how can we start to think about uncertainty quantification? We know that they definitely, we know they will have trouble measuring tidal turbine wakes, and they will have trouble measuring really dynamic areas of the flow, and there are lots of really dynamic areas of the flow. So what we said was, what if we could turn that on its head, and instead of having our instrument on the seabed pointing up, we have multiple instruments pointing to one location. That gets round some of these limitations of the technology. And ADCPs are the standard used technology at the moment for trying to understand dynamic environments for ORE. So we have custom novel sensors. We make them if we have to, and we've developed multiple prototypes of what we call converged ADP, CADP. And this is a cartoon of how we planned to do it on the Realtide project before COVID came along. So we ended up having to think on our feet and rework the plan. The concept started here, as you can see on the left. It's like most of these things, starts with a sketch or an animation, like videos. It won't play, I don't think, but what's happening here is, what if we could also move the beams? Because then we could build up high-resolution maps, not limited by the limitation, and we could operate it autonomously. To do that, we need phases, and I think I call this engineering Scrabble, because on the report, everything's all nice and phased. You de-risk everything perfectly. In reality, in research, it's a lot of luck. Did you win the bid? Did you not win the bid? Is your PhD student up for a trip to America? Can you get a travel fund? That sort of thing. And you split as your opportunities come up and as you have ability to piggyback on deployments and things, and you try and come up with a strategy that will get you to your objective. And for me, it's never been linear. I'm sure it's similar for others. Here's a top left. It's quite nice. That's Mary Dorward, recently completed EngD student. She actually was funded by the ETP Travel Fund to go to Washington to carry out this experiment with our partners at the DOE funded lab PNNL. So we were able to say, okay, while we wait on working out what's happening on the European project, let's go to America and learn some subsystems. I'll play this video. And what we've actually done is, that was a subsystem so we could test the full-scale device. And can we get this rig in UK waters now that we couldn't deploy in France? And hopefully it will play. I think it will. It played on the... Here we go. Sorry, it's a bit shaky. This was a coffee-fueled mobile phone footage that's coming up, I think, of us trying to get ready. And we were against a tide window and an important one, the project was closing window. So this was mitigation and a bit of a replan. That's actuated sensors. They're sensors on actuators. We had to test it mechanically. This is at the King's Buildings, just where we're building our new engineering building. We had some space, which was great. This is up in EMEC. Thanks to EMEC for their collaboration on this. You can see the frame here where this footage is probably the bit best to show it. This is drone footage. It's about 9 meters diameter, 4 tons dry mass. It's got 6 of our converged sensors around it. It's got partners' prototype instruments on it so that they could learn. And it's got a standard off-the-shelf instrument for baselining as well. It's been lowered here onto a leased marine vessel, funded by Realtide, amongst other projects. and that's us going out to sea. There's quite a few different tests here. We've got inertial measurement units on this. We've got accelerometers and pose sensors, so we know the frame's orientation. We're really interested in being able to calculate how it's landed, make corrections through the actuators, and then focus on different parts of the sea. And we're heading out to about the location of the orbital device to collect the data. It was down for about 6 weeks, and we collected some storm data in there as well, which is important for the wave current interaction that you saw earlier on. And I think I stop it just as it hits the water in the interest of time. We did have ROV footage as well, go down to check that lights were blinking and things. And we don't want to do this all the time. I should say this isn't to replace the off-the-shelf instrumentation. This is to get transfer functions and calibrations and uncertainty quantification. So finish up. I've got through this faster than I thought I would when I was scanning this on the train on the way through. We've done lots of research activities at sea. We don't mind the method. Lots of the time it depends on who you're working with. We've used ROVs, we've used just ropes, hydraulic release shackles, and even on it with our French partners, we've used divers, which I've never seen done in tidal sites with flow speeds and depths in the UK, but in France they were able to use a dive team. So we actually have recovered instruments mid-deployment, and we've recovered instruments from turbines using dive teams, which is quite different when you do your engineering design if you think you've got people available. I've worked with developers over the years. We did a lot of instrumentation. Top left, that's the Deep Gen 4, the REDAPT machine. Sabella D10 in France, and currently our instruments are installed on the Orbital O2 device as well. And we have ND and PhD students embedded with the companies where we can as well. It's quite holistic. We developed some of the sensors in the tank. Here's some pictures of the flow wave facility at the University of Edinburgh, where we can have combined waves and currents up to about 1.1 metres per second. So that's actually fast enough to do quite a lot of work there. We test machines. Top right was a project that I helped coordinate. A big team of postdocs. We had 6 or 7 of us working on that to get the first array of tidal turbines out. And they're actually scaled machines of the big Deep Gen 4 that you saw. And I've tested in tanks all across Europe as well for helping out on other collaborations. The important thing that we're working on now, and it's one of the main lessons learned, is, and actually feedback from industry as well, is that a lot of the academic tools are very difficult to pick up, or they're very difficult to keep running with. Data gets lost. Tools can be too complicated. The expertise required to run a fully coupled atmospheric wave current simulation, for example, is quite a high bar. We've been working on trying to get fit-for-purpose tools and make sure that they're available and can be used and can be picked up. And one example is that we're working on at the moment is, can we get our new PhD students up to speed with modelling in weeks rather than a year? This is the step change that we are trying to do. How much time do we need to buy out of our staff team to train them with off-the-shelf tools and guidance and videos so that we can really accelerate that? And we're trialling that with our PhD students as beta testers at the moment, so that we can start answering more questions rather than spending a lot of the time chasing signals and chasing data. And we're working with our partners, industrial, on that as well. We are, as I say, building towards collecting our data in a better way, making it publicly available, and trying to make it collaborative. So the QC, the quality control, can be updated and iterative and community-based, if you like, to keep the data alive rather than archived. But for that, we're partnering. We do have a website, but it's we're waiting till we transition it to, it's open, you can go have a look at tidalenergydata.org, but it will be getting updated. And lastly, just to finish, I think I'm just about time, your journal papers and your technical reports and things, they have pictures of kit, but they tend to not have the actual people who make it happen, and I think that's really the key. It's been 10 years of working in this across different streams, and really that's all about trying to collaborate with people. There's a picture down here of some of the people we've worked with, students, technicians, insurance people are really good to speak to if you're in this area, and lawyers, of course. And then lastly, to finish, as we get more and more multidisciplinary and as we move to bigger and bigger projects in this area, here is the kick-off picture where we were in Greece for the Iliad project. It's an European project I'm involved in. We're looking at digital twin of the ocean, so we are pilots under that. But the overall theme is digital twin of the ocean. So yeah, we're going to need a lot more people and a lot more collaboration to keep that going. And thanks to all the people who've helped, thanks to the project partners and to the funders over the years and to the CDTs that have been involved in. And I think that's
brilliant,
that's
Brian.
me, so thanks very much.
The late lamented Pecker scheme, eh? Such a small amount of money for such high impact. Right, so does anybody have any questions for Brian? Jonathan, what about you?
Were you sleeping?
Jonathan.
Thanks for that, Brian. That was a really interesting talk, and great to see the range of projects you've been working on since I've seen you last. And the access that some of the projects that you're providing have provided to the amount of data that's been generated over the years. What impact do you think the increased access to other people's data can have on the next generation of testing and design projects?
It's a good question. I think it's actually related to that circle, the diagram of the data is linked to all the different tools. I think we need tools and we need to ask questions. Just the data isn't enough. You need people as well. And so where I think the gap there is in almost the knowledge transfer, the training, and the ability the flexibility to deploy the right people to the right time, to buy out somebody for a week to go answer a question rapidly, which they could do, but they probably can't because there is either not a mechanism to do that, or we've not recognised, we don't think that you can trace the impact through or something. So I was thinking about this on the train on the way in, actually. I think it's more about being able to deploy the people that know the data or that know the tools. You have to look after the data first, though. So if you don't, the old standard used to be portable hard drives, and we've had a recent example of a portable hard drive was the last resort of some really important data that was lost, and with project partners. So we're doing better than that now. We've got archival tools, but we found that it's not just, even having them archived isn't enough. Somebody goes and downloads the whole lot, they send their PhD student off for 18 months looking at it, and then you find out that, if they just picked up the phone or emailed, you could have made much faster. So it's about speed, and being able to, so I think, yeah, data, we have to fix it first, and then it's what we build around that. And I think similar for the tools, we have developers who just, there's a barrier to using the tools we've already invented. So how we bring that together is a bit of a challenge.
Okay, thank you. Anybody else? Final question? Is anybody? No? Okay,
Nope.
in that case,
Thanks
please put
very
your
much,
hands together for Brian. Thank you very much.